So how do we capture the notion of received signal quality? If the quality is high, you'll be able to talk more efficiently. For example, you can talk faster and the receiver can still understand what you're talking about. But sometimes in cocktail party, because it's so noisy around, so much interference, you have to slow down your conversation. You have to talk slower, that is fewer bits per second, so that the receiver can hear you correctly. And the way we capture this ratio is through the so-called SIR, signal to interference plus noise ratio. Now, what is the signal? I'm not talking about the signal power at the transmitter side. I'm talking about the signal power at the receiver side. So that is the transmit power, which we denote by P sub, let's say I, P sub I, multiplied by the channel, that's the direct channel, getting to the receiver of pair I. That's the received power. Divided by, because it's a ratio of the interference collected at the receiver. That is P sub j times Gij, okay, from jth transmitter to the same common ith receiver. And there are many of such j's not equal to I. Plus, at the ith receiver, there's usually some noise term, n sub I. This is what we call the SIR associated with the ith user. For example, in our previous case, we have just two users, and therefore SIR1 is simply P1 G11 over P2 G12 plus N1. And also SIR2 is just P2 times G22 over interference, which is P1 times G21 plus N2. Okay, but in general, you have more than one term here in the denominator. Okay, so now that we have the notation, let's look at what kind of a function this SIR is. SIR for each transceiver pair I, okay, the received signal interference ratio for pair I is really a function of the entire vector, with this notation on top, of power vector P. Okay, it's not just a function of your own power, but also a function of others' power. That is the mathematical representation of the very physical fact of interference in wireless communication. If there's no other user, it's easy to increase SIR for user 1. I'll just increase P1. But of course, there are other users. A larger P1 helps SIR1, but it will also show up as a larger denominator for the other SIRs that will hurt the other SIRs. Okay, so first observation is that SIR is a function of the entire vector P. Now second, what are the constants and what are your degrees of freedom? Because we're talking about transmit power control, so obviously the degree of freedom is the vector P. That's what we want to design and optimize over. We are given all the Gij's. That is determined by the propagation environment. Okay, is this indoor? Is this outdoor? What kind of terrain is it? It is given by the location of the transceivers. And that's not up to us to optimize. And we are given all these receiver electronics and therefore their noise. So the G's and the N's are given constants. The P's are what we'll be calling the optimization variables in transmit power control. So now our goal is to say all different transceiver pairs indexed by I would like to get a certain SIR achieved. Okay, so the question is, for a given set of G's and N's, can we find such a vector P? Is there such a vector P at all to achieve certain target SIR values? And if there's more than one, which one shall we pick? In the next module of the video lecture, we will see the answers to these questions in a distributed mechanism to coordinate interference in wireless cellular networks, and that mechanism is now in use in many wireless standards.